So our learning objective is to compute the 5-number summary, and our second objective is to draw and interpret box plot. So when we say the 5-number summary, it involves Q1, which we know how to calculate it. It involves median, which is the same as Q2. It involves Q3. And the beginning of it, the first number that has to come before Q1 is your minimum data value. So just go through your data values, look for the minimum or the smallest data value that goes here. And then go through your data values again. What is the biggest or maximum data value that goes here? That makes up the 5-number summary. So 5-number summary is just the smallest data value, then Q1, then the median, then Q3. And lastly, we have the largest data value. So we organize it as minimum, followed by Q1, then followed by M or Q2. M is the same as median, then followed by Q3. And lastly, we have the maximum data value. So we are going to look at an example where we are asked to organize or to write our 5-number summary. So this is an example on obtaining the 5-number summary. So every 6 months, the United States Federal Reserve Board conducts a survey of credit card plans in the US. The following data are the interest rates charged by 10 credit card issuers randomly selected for the July 2005 survey, determining the 5-number summary of the data. So since we know what is meant by 5-number summary, and obviously we'll be looking for Q1, Q2, Q3. Our very first step is to arrange these from smallest to highest if they are not already arranged. So these are the interest rates. You can see that they are not arranged from smallest to highest. So we just have to arrange. If we arrange, we are getting it as 6.5 being the smallest, followed by 9.9 in that order. So we get to the last one. So this last one is the biggest. So that's the highest or the maximum from smallest to highest. We know from yesterday that if we want Q1, Q2, Q3, we first have to find Q2. We are going to find Q2. The minimum and maximum, those are, since you have arranged them from smallest to highest, those are the ones at the end here and the other end. But what is important for us to be able to get it right is the Q1, Q2, Q3. So from here, we are going to find Q2. So we know that this one here will take care of this. This next one will take care of that. This will also take care of that. This takes care of that. Because we had our N to be even, I think we have about 12 of these. We have our N to be even. It means we are going to expect to have 2 numbers in the middle. So these are the 2 numbers in the middle. We just take those 2 numbers, add, and then divide by 2. So when we add and then we divide this by 2, those of us who have calculators, we will realize that we are going to get our Q2 to be 13.6. So that is Q2. So Q2 is 13.6. And we got that because we have these 2 middle numbers. We need to add and then divide by 2. So after you have gotten your Q2, what you can do is you can just bring it here as part of the data. Now it has to be a number between these 2 numbers. We have it as 13 points. Now go to the left side of 13.6 and look for the median of those numbers on the left side. So these are all the numbers on the left side. So this will cancel out this cancel this. So now this is the median of the numbers to the left of Q2. So this 12 becomes Q1. So now we have Q1 and we have also been able to get Q2. Now we have to find Q3. To get Q3, go to the right side of your Q2. These are all the numbers on the right of Q2. And then we find the median of those numbers. So this will take care of this. This also takes care of that. So we are left with 14.4, which is in the middle. And that is our Q3. So in summary, we have Q1, which is 12. We have Q2, which is 13.6. And we have Q3, which is 14.4. And the smallest data value here was 6.5. And the largest was 14.5. So this makes up the 5-number summary. smallest data value, then Q1, Q2, Q3, and the largest data value. Very simple. If such a question is on the exams, we should all be able to do it. It's not that difficult. So after we have gotten our 5-number summary, we can use that 5-number summary and other information to draw what we call a box plot. So a box plot is like a graphical representation or graphic, a picture which is showing or summarizing the 5-number summary. And it also gives us information about our outliers. So apart from summarizing the 5-number summary, it also tells us about outliers. So we are going to learn how to draw a box plot. As the name implies, there has to be some sort of a box somewhere. So our first step is to determine the lower and upper fences. So we came across, I believe we came across this yesterday. Based on the lower fence and the upper fence, we were able to determine what our outliers are. The example we did yesterday, there was no outliers. So we are going to draw the lower fence, upper fence. To draw your lower fence or to determine your lower fence, you have to get Q1, which we all know how to do it. After getting Q1, we have to find IQR. And yesterday, can someone remind us how we find IQR? IQR is the same as interquartile range. Does anybody remember the formula or how we find IQR from yesterday? Does anybody remember? I'm going to give you a hint. You have to subtract one of the quartiles from the other. So does anybody remember how we find IQR, interquartile range? Does anybody remember from yesterday? That was
you take Q3 minus Q1.
Perfect. Thank you so much. So that is interquartile range. So as we move on in the semester, we always build on what we are learning. So please let us not forget what we learned previously. Thank you very much for that answer. So IQR is Q3 minus Q1. So since we have already calculated our Q1, Q2, Q2, you are just subtracting Q1 from Q3, put it here, multiply by 1.5, then we subtract from Q1. We did this yesterday. And then for upper fence, just like this upper, so you're looking at the bigger numbers. That's Q3 plus 1.5, then times IQR. So if you are using the same data set, then whatever value you are getting for 1.5 IQR, that's the same value you are using here. So that's just get that value, calculate that value, subtract it from Q1, then calculate that same value that you got from here, just add it to Q3. So just do this first. It is multiplication. Multiply first, get that product, subtract it from Q1, use that same product and add it to Q3 because this is the same as this. The only changes is with Q1 and the minus Q3 and the plus. So IQR is already written here, Q3 minus Q1. Then after we have been able to get these fences, we are going to draw a line long enough to include the maximum. So this is the first step in drawing a box plot. Get your lower fence, upper fences, then draw a line long enough to include the maximum and minimum values. Then we insert vertical lines at Q1 and then at Q2, then at Q3. And we put those vertical lines in a box. We are going to enclose those vertical lines in a box. Then we will label the lower and upper fences. So whatever value we got here, we are going to label it. And then whatever value we got here, we are going to label it. After that, we draw a line from Q1. So we know Q1. We draw a line from Q1 to the smallest data value that is larger than the lower fence. So go to all your data values, look for the smallest data value that is larger than the lower fence. We are going to draw another line, this time from Q3. And from Q3 to the largest data value that is smaller than the upper fence. And these lines that we are drawing a line. So these lines we are drawing, we call it whiskers. Just like if you have a cat has whiskers. The same way Boxplot has whiskers. So the lines we are drawing from Q1 to the smallest value that is larger than the lower fence is one whisker. And the second whisker is to draw a line from Q3 to the largest data value that is smaller than the upper fence. Then any data values that we think are less than the lower fence or any data value that we think are greater than the upper fence are called outliers. We did outliers in 3.4 yesterday. So whatever you got from here, if there is any data value that is smaller than this, that is going to be considered an outlier. If there is any data value that is larger than this, that is also an outlier. When we are drawing box plot, we use asterisks to represent our outliers. So if you see any asterisk, just look for the number corresponding to that asterisk, and that is your outlier. So with this in mind, we are going to do, we're going to draw a box plot, and we'll follow these steps one by one. So we are using these steps to draw our box plot. So obviously we know it involves Q1, Q2, Q3, and the rest, so we still have to know our Q1, Q2, Q3. We are using this same example. This is the example we just did where we found Q1, Q2, Q3, we found the maximum and the minimum. So we already know what Q1 is from that question. That is what we did here. So let me just so that was our 5-number summary. And we are going to use that 5-number summary and other information to draw our box plot. These are our 5-number summary, which I have brought here just to guide us. So we have our 5-number summary. And from this 5-number summary, we are going to use that to draw our box plot. I'm making it red so that we know that that is just the 5-number summary. So according to the steps in drawing a box plot, the first one is to look for your lower fence, upper fence. So as we look for lower fence, upper fence, we are using IQR. That means we have to find IQR. So this is our Q1, and then this is Q3. So IQR is going to be Q3, which is 14.4, minus Q1, which is 12. When we subtract, we are getting 2.4. So now we have IQR, which is 2.4. Our next step is to find lower fence, upper fence. Because it's lower, we are using Q1. Q1 is always smaller than the Q3, smaller than the other two Qs, smaller than that. So we are using lower, so use the smaller one. So that is 12. And because it's lower, we are subtracting. So minus 1.5. And our IQR is what we got as 2.4. So multiply, do this first. So do the multiplication first before you go and do your subtraction and addition. If you have calculator and you multiply 1.5 by 2.4, you are going to get that to be 3.6. So we have here to be 3.6. Subtract it from 12, and that will give us 8.4. That is our lower fence. Take that same 3.6 and then add it to 14.4. 14.4 is Q3. If we add it, that gives us our upper fence. So now we know our lower fence, we know our upper fence. That is the first step in the construction of a box plot. So the second step says that go ahead and draw a line long enough to include the maximum and minimum values. So we know our maximum values, we know minimum values, and then we will also do Q1, Q2, Q3 and put it in the box. So now that we know our lower fence and upper fence, we are going to look at the minimum and maximum. So the minimum was 6.5. So we are going to draw like a number line. So this is like a number line, and with the number line we are drawing should be long enough to include the smallest data value and also to include the largest data value we have in the list of data values. So in our list of data values, when we arrange from smallest to highest, we got the highest to be 14.5. So as we draw our number line, we should make sure that it accommodates the 14.5. And then from here, we can draw our smallest and largest. So the smallest we have is 6.5. And then the largest we have is 14.5. So this is your 14. So this is 14, this is 15. So the highest is going to be 14.5. Which is going to be somewhere here, 14.5. And the smallest we have is 6.5. The 6.5 is also somewhere here. That is the second step. Second step said that we should draw a line long enough. So a line long enough to include the maximum and minimum value. So that is our line here that we have. This is our line. And then from here, we can also go ahead and then represent our Q1, Q2, Q3. Q1, we got that to be 12. So we just draw a vertical line here, which is Q. And then Q2, we got that to 13.6. So still on the number line, 13.6 going to be just a little above or a little beyond 13.5. So this line you see here, this vertical line is Q2. Then Q3 is what we got as 14.4. It is going to be a little before the 14.5. So this is Q3. So after we have drawn this vertical line, we enclose it. Let's close it for it to look like a box. So that is the second step. We're able to draw our horizontal line. That is like a number line, which will include the minimum and the maximum. We've been able to draw our box. At this point, the next step that follows, if you are looking at the steps for drawing our box plot, the next one says that we should go ahead and label the lower and upper fence. So our lower fence, we got that to be 8.4%. So we go to a number line again. We are looking for where we can see 8.4. 8.4 will be a number which is between 8 and 8.5. So all the ones you see in between the whole number, those are like 0.5. So 8 and 8.5, just a little before 8.5. Because it's fences, those of you have your houses with fences. With our fences, if you are just imagining, they look like this. So because it's fences, we are going to use like a bracket to draw our fences. We are labeling our lower and upper fences. Our lower fence, which we calculated, was 8.4. And we just realized 8.4 is going to be somewhere here. So we just draw it like a fence. So this is the lower fence. Upper fence obviously is going to be bigger than the lower. So that is 18. But because we were drawing our number line and we made it to the highest, which was 14.1, now you need to extend it to accommodate the upper fence. So upper fence is 18. So we elongate our line all the way to the upper fence, which is 18. Then again, we draw our fence here. So now we have our upper fence and then we have our lower fence. Then the fourth step, if you are following the steps of drawing our box plot, then the fourth step says that draw a line from Q1. This is our Q1. We are going to draw a line from Q1 to the smallest data values. Let me take you to the steps again. It says that draw a line from Q1 to the smallest data value that is larger than the lower fence. So we are going to our original data value. We are looking for the data value from here, which is the smallest data value that is larger than our lower fence. For lower fence, we were getting that to be, so let me go back to, I think we got that to be 6.5, just to be sure. Let me go back to our calculation. For our lower fence, 8.4. Our lower fence, we got that to be 8.4. This is our lower fence. So now we are going back to our original data set. In that original data set, we are going to insert 8.4, and then we will look for the smallest data value that's larger than 8.4. This is our data values that were given. We just realized that our lower fence, when we calculated, got 8.4. We are now going through this data set. We are looking for the smallest data value that is larger than 8.4. Smallest that is larger than 8.4. Looking at this, if we were to put 8.4 here, we can see that we have a lot of data values which are larger than 8.4. 8.4 is your lower fence. We have a lot which are larger than 8.4. So the statement said, look for the smallest data value that is larger than 8.4. So since we have a lot larger than 8.4, we are looking for the smallest of them. All these are larger than 8.4. But which one is the smallest? The smallest will be 9.9. So that step says draw a line from Q1 to 9.9. We got 9.9 because it is the smallest of all the data values that are larger than 8.4. So that is, excuse me, that is 9.9. So don't forget 9.9. We'll go and continue with our box plot very soon. But 9.9 is the smallest data value that is larger than 8.4. The one that follows says that we should continue to draw a line from Q3 to the largest data value that is smaller than the upper fence. When we did our upper fence, we got that to be 8%. So now we are looking for the largest data value that is smaller than the upper fence. Upper fence is 18. So looking at what we have here, we don't even have 18 as part of the data value. And we want the one which is, we are looking for the largest data value that is smaller than the upper fence. Looking at all, these are all smaller than your upper fence. They are all smaller than 18. Out of all these which are smaller than 18, which one is the largest? The largest will be 14.5. 14.5 is the largest. So step 4, where it wanted us to find the smallest data value that is larger than the upper fence, larger than the lower fence, we got 9.9. And then that same step 4 says that we should look for the largest data value that is smaller than the upper fence. Upper fence is 18. That would have been somewhere here. And looking at all these data, they are all smaller than 18. But which one is the largest? The largest is 14.5. So we are going to draw a line from Q3 to 14.5. Then we draw a line from Q1 to 9.9. So we are going back to our box plot. When I finish, I'll do this on the whiteboard again to explain to you. So going back to our box plot, which we were drawing, now we can see that we have to draw a line from Q1 to 9.9. So this is our Q1. We are going to draw the line from Q1 to 9.9. 9.9 is going to be just a little up and before 10. So that is going to be a point somewhere here. And we are drawing a line from Q1 to 9.9. Then we do the same for the upper fence. So for upper fence, we got, when we're looking for that value, we got that to be 14.5. So now we go to Q3 and we are drawing a line from Q3 to 14.5. This is Q3. Q3 was 14.4, and we have to draw a line from 14.4 to 14.5. So that is a small line, a small distance. Distance of 0.1. So that is from Q3 to 14.5. So at this point, we've been able to draw our Q1, Q2, Q3, which is put in the form of a box. We've been able to label our lower fence, upper fence. We have been able to draw a line from Q1 to 9.9. We've also been able to draw a line from 14.4, which is Q3, to 14.5. The last step, if we are looking at the step, the last step is where we find outliers. So the last step here is any data that is lower than the lower fence or greater than the upper fence are considered outliers. So our lower fence is what we got to be 8.4. So we go back to our original data set and then we check to see if we have any data value which is less than 8.4. So this is our original data set. You can see from here that we have a value which is lower than 8.4. Any value which is smaller than lower fence is considered outlier. If we are to put 8.4 somewhere here, to that been here. So any value smaller than 8.4 is outlier. So straight away 6.5 here is considered an outlier. If it is an outlier, we use asterisk. So we go back to our box plot and then we put asterisk here. So that asterisk here shows that this is our outlier. Then we check the upper. So any value which is bigger than the upper fence is also considered outlier. So we go back here. We don't see any value which is bigger than 18. There is no value bigger than 18. So since there is no value bigger than 18, we don't have outliers on the right side, but we rather have the outlier on the left side. So if it is an outlier, we use asterisk. We use asterisk. All right, so I'm going to do this all over again on the whiteboard because Here it was already done for us. So let me write this Q1, Q2, and the rest down, and then that's the information we are going to use. So Q1 we got 12.0 for Q1, and then for Q2 we are getting that 13.6. For Q3 we are getting 14.4. Maximum is 14.5. And then the minimum we got that to be 6.5. And the value that was smaller than the low, smaller than the lower fence was what we got to be 9.9. So that's step 4. We were asked to look for the smallest beta value that is larger than the lower fence. That's 9.9. And for 14.5, that is the largest beta value that is smaller than the upper fence. We got that to be 14.5. For our lower fence, I'm not going to calculate them again on the whiteboard. You already know how we did this calculation. So for our lower fence, we got that to be 8.4. For our upper fence, we got that to be 18. So we are using this information to draw the box plot. So now I'm going to draw the box plots by hand. So I'm going to share the white screen or the whiteboard with you, and we can draw the box plot. So these are the information that we have. Our minimum is 6.5. Then we have Q1, which we got that to be 12. Q2, we got that to be 13.6. And then we have Q3, which is 14. And for our maximum, we got that to be 14.5. And also for lower fence, which I'm writing as LF, we got that to 8.4. And then for upper fence, we got that to be 18. And when we were looking for those values, so when we're looking for the smallest data value, that is larger than the lower fence, we got that to be 9.9. And when we're looking for the largest data value, that is smaller than the upper fence, we got that to be 14.5. These are all the information that we need in order to draw our box plot. So from here, we are just going to draw the box plot. So we are going to draw a straight line or a horizontal line here, which is like your number line, long enough to have the minimum and also to have the maximum. And as we realized, it should be long enough to also have the upper fence. This is upper fence. So we can just decide to make it of differences of 2, 2, 2, or differences of 1, 1, 1, whichever you want. So we can start from 6. And then we will have here to be 7. So I'm making differences of 1, 1. Then we have 9, and we have 10. I hope I have enough space. Then 12, then 13, and then we have here to be 14, all the way to 18. So this is just a sketch. You saw the correct one on this. So spacing some are bigger than the rest. Now start all the way from here. So we have 6, then followed by 7, then 8, then 9, then we have 11, then this will be 12, 13, 14, 15, 17, and then 18. And then from here, as part of the steps, we have to find the upper fence, lower fence, which we have already done. So we got, as we did on the PowerPoint, we got lower fence to 8.4, upper fence is 18. And from here, we are going to check to see if we have included the maximum and minimum. Minimum is 6.5, it should be somewhere in between here. And then the maximum is 14.5, which we can see like we nice somewhere here. So now we look for Q1, Q2, Q3. Q2 is, Q1 is 12. So just draw a vertical line here. And then Q3 is 13.6. 13.6 will lie in between these two. So just gauge or just imagine where it's going to be somewhere here. And then we have Q3, which is 14.4. That is like somewhere 14.4. Then we enclose this in a box. So we have it as a box. This is Q1, this is Q2, and then this is Q3. After that, after we have been able to label, the next step is to label your lower and upper fence. So fences are drawn like a bracket. So our lower fence is 8.4. It's going to be somewhere here. So we just bring a fence here. Our upper fence, we got that to 18. So this is 18. So we just bring like a fence here. That is our third step. Fourth step is where we are asked to draw a line from Q1 to the smallest data value that is larger than the lower fence. So we realized that there were lots of data values that were larger than the lower fence. But out of all those values which were larger than the lower fence, the smallest of them was 9.9. So we go to Q1 and we are drawing a horizontal line from Q1 all the way to 9.9. So 9.9 would have been somewhere close to the 10. So we're going to be somewhere here. So from Q1 all the way to 9.9. This should be a straight line. Sorry, this is crooked. It should be a straight line. Then we are also going to draw another line from Q3 to the largest data value that is smaller than the upper fence. There were a lot of data values. All the data values that were given were smaller than 18. But out of all those smallest values that were smaller than 18, which of them is the largest? The largest is 14.5. So we draw a line from Q3 to 14.5. Q3 is already 14.4. So if you are drawing to 14.5, then that is just a small line. That's to have like a 0.1 distance. So that is our whiskers. This is what we call whiskers. From Q1 to that value is a whisker. Then from Q3 to that value is a whisker. Our very last step is to look for the outliers. So to look for outliers, we consider our lower fence, and then we are looking for all the values in the data set that are lower or that are smaller than our lower fence. So from our original data, we realized that the only value that was smaller than 8.4 is 6.5. So now we go to 6.5, which we know is going to be somewhere here. And then that is an outlier. Outliers are represented with asterisks. So that would be an outlier. Now we go to the upper fence. We look through all our data values. Which of these is larger than 18? Remember, our maximum is 14.5. So there is none that is larger than 18. Even the upper fence itself is larger than our highest data value. So on the right side, we did not have any outlier. There was no data value that was larger than 18. So this is what is considered as a box plot. You can see in the form of a box for the Q1, Q2, Q3. We have our whiskers here. And in addition to the whiskers, we can also see our fences. And we also have our asterisks here to show that this is an outline. So anyone who looks at this knows that the value that we drew corresponding to this is the outline. Sometimes you don't have to do all of this work. Sometimes the box plot will already be drawn for you. It would have already been drawn, and then you will have to answer some questions. So if you are fortunate and your homework is already drawn and it asks you for Q1, just trace it to the horizontal, like your x-axis, the horizontal axis, look for the value here, and then just trace this. That will correspond to Q2. This will be Q3. And then if it asks for the lower fence, upper fence, this is your lower fence. So just trace it down here. This is upper fence, just trace it down. If it asks for the outline, just trace it down. And the value corresponding to it is going to be your corresponding values for whatever percent it was asked. So this is what is meant by a box plot. We have a box plot. We can look at the shape of the box plot and determine whether it is skewed left or skewed right or symmetric. So for example, like in this case, just look at the whiskers. If you want to determine whether it's skewed left or right or the rest, just look at your whiskers. You can see we have a longer whisker on the left, while on the right side we have a shorter whisker. So the longer the whisker or the longer of these ones is going to bear the name. So since the left side has the longer whisker, this is skewed left. The longer one is on the left side, skewed left. If this one was rather longer and it's on the right side, that would have been skewed right. So that is what we are going to look at next on our PowerPoint. Please, if you have any questions, like I always say, you can stop me and then ask your question. So this is the proper box plot. What I will say is just a sketch. So from this, we can see that we have the longer tail here, and the longer tail is to the left. So that means this is skewed left. And then we have this. All right, so now let's look at what I was referring to. So assuming that we had our data, based on the data, we draw our histogram, we got this, and we got another histogram and another histogram. If we were to draw box plot corresponding to these histograms, this would be the corresponding box plot for this histogram. This is box plot for that histogram. This is box plot for that histogram. We are going to use a box plot and quartiles to describe the shape of a distribution. So looking at this first one, if this was the box plot corresponding to this, even without the box plot, we know that if it is in the form of a histogram, we can draw our shape, and then we can also determine the distribution. So if we draw like a curve around this, we already know that this even doesn't have a right tail, left tail here. This is skewed to the right. So in that case, the longer tail, and it corresponds towards the box plot. The box plot has the longer tail to the right. So this is skewed right. The same way we can see the peak is in the middle. So if we were to draw our curve around this, realize that from the peak to the left and from the peak to the right, the distance is almost the same. So this is symmetric. And it also confirms from the box plot. The distance from here to here is almost the same. If not the same, then it's almost the same. That is symmetric. And the same applies here. If we were to drop our curve around it, you realize that we have the longer tail to the left. The same one is similar one is what we see with the box plot. So the longer tail is to the left. So that's left. So based on, oh, sorry. Michelle, did you say I was cutting out? Oh, I'm so sorry. Am I cutting out to all of you or just Michelle? Is it for all of you?
Yes, you're cutting out.
Oh, I'm so sorry. I wish you had told me earlier on. I'm so sorry. Sorry, let me turn my hotspot on. I think I'm connected to my home internet. Let me turn the hotspot on. Maybe that will make it better. I'm so sorry. I didn't realize that was happening.
It's just like a split-second lag, but yeah, it can be
okay. All right.
distracting.
Okay. All right. Thank you. Thank you for informing me. Yes. So, was it just for this slide? It was when I was just explaining this slide, right? So that if that is the case, let me go back and explain this slide again. I think that is where I started cutting off. So let me connect to the hotspot real quick. Just a minute. Let me connect to you. Okay, so I'm now connected to the hotspot. Hopefully, I don't get cut off again. All right, sorry about that. So we are using our histogram, and most times, since you are drawing the box plot, you will not even have access to the histogram. But this is from a data which we don't know. Based on the data, this was the histogram, this is the box plot. And we realized that if we were to draw our shape around, this would be skewed right. And the box plot that was drawn out of that also shows that we have skewed right, because the longer whisker is to the right, so skewed right. But how your questions will be structured in such a way that it will tell you to draw your own box plot. After drawing the box plot, now it will ask you what is the distribution or what is the shape. So in that case, just look for the longer whisker. This one is the longest one is on the right, so skewed right. But this would have been a histogram corresponding to it. Here we can see that if we were to draw the curve around this from the peak to the left and from the peak to the right, you realize that it should be almost the same distance, and that confirms our box plot. So if after drawing your box plot and realize that the whisker here is almost the same distance as this, then it means it's symmetric. And if after drawing your box plot, you realize that the whisker has a longer tail to the left, that is given. And if we had drawn the histogram, this would have been the corresponding histogram of that data. So that is about the 5-number summary and box plot. And that brings us to the end of chapter 3. So chapter 3 we have from section 3.1 all the way to 3.5. And 3.1 was numerically summarizing data. So if you have any question, you can please ask before we move on. Any question, you can please ask. If no question, then maybe as you do your homework, it will make more sense. So because because my math lab is down, I'm going to extend all the homework. I had already used it because I realized there's a lot of sessions that have been taught. So now I'm going to extend them till next week Friday because it is down. So when it comes up, or if I'm able to log into my account, I will extend. Okay, I'll extend all of them. I think I'll extend some of them, but I'll extend all of them. Please do not procrastinate, because if you decide to leave all of them to next week Friday, next week I'm going to add more information, so that'll be too much. So as soon as it comes up, please start working on them. And yesterday, those who were here for the group work, those who joined for the group work, I haven't added your 5% yet. I'll add it today. If I am able to log into my account, I'll add the 5% to your first quiz. So I'll add it to first quiz. Now let's look at chapter. Descriptive statistics. We are describing, even if it already says describing. So we are going to describe the relation between two variables. So in this case, we are not looking at just one variable, we are looking at two variables. So if you are asked to describe the relation, how are you going to describe it? And since it's two variables, it's similar to the things we learned in intermediate and elementary algebra. In elementary algebra intermediate, you have like your x and y values, you draw your table, and then this is your x, this is y. Assuming you were asked to draw the line y is equal to 2x plus 4, then you have to get your own x values, put it here. Based on the x values, you try and get your y values. All right, so Alisa, I'm going to extend the homework. That is everything I taught this week. I'm going to extend it till next week Friday. Not this Friday, but next week Friday, because the system is down. So because the system is down, I don't want to put too much pressure on yourself. I'm going to open it till next week Friday so that you have enough time to do it. But at the same time, all of you, please do not wait till next Friday before you do your homework. Because this week alone, I think I've taught about 5 or 6 or 7 sessions. So if next week I bring about 5 more sessions, that should be like 12 or 10 sessions, and it will be too much to do all of them on next week Friday. So please make sure that as it comes up, you have one at a time. Maybe a day you do about 2 sessions on homework on. So just make sure you schedule it so you have enough time to do. Don't let it be too much of this. All right. So next week Friday, I'll put it on the announcement when I put it on Canvas. So in this session, we are looking at two variables, how we are going to describe it. This is similar to some of the things we learned in intermediate algebra and elementary algebra or in high school. If you are asked to draw this line, you just make your table x and y. Those some of us will use rise over run, others will make tables and then get our x values like -1, 0, -1, 2. Based on that, we plug these values in place of x and get the corresponding y values. In that case, you are getting x and y values, x and y, and that is exactly what we are doing in chapter 4. So in chapter 4, we are representing some of the things we learned in algebra, and then we'll apply it to statistics. So in this chapter, we'll discuss graphical and numerical methods for describing bivariate data. And when we say bivariate data, because of the word bi, it means that we are looking at two. So that is a data in which 2 variables are measured on an individual. So it should just be one individual. This same individual, we want 2 variables to be measured on that person. It can be that you just decide to choose, you don't want your weight and your height. So if it's that one individual, we are interested in that person's height, we are interested in that person. So that means we have now X and Y on one individual. So by variance, we are looking at data on that same individual, but it has to be two variables. So that is what we are doing in this session. We are doing our X and Y. So our learning objectives are we are going to learn how to draw and interpret scatter diagrams, and then we'll describe the properties of linear correlation coefficient. Then we'll compute and interpret the linear correlation coefficient. And lastly, we'll determine whether a linear relation exists between two variables. So those are the things we'll be doing in this session. Like I said, we are looking at graphical and numerical method for describing bivariate data. And bivariate data or data is a data in which two variables are measured on an individual. Example can be if we want to decide to determine the amount of soda. I know some of us drink soda a lot, so if we want to know how amount of soda that is consumed per week is related to one's bone density. I'm not a biology student or a medical person, but if you want to know how the amount of soda you consume per week is related to your bone density, then we can look at you, the individual, and then you, the individual, look at how many soda you are consuming a day. We want it per week. So because it's per week, we know we have 7 days in a week. So day one will come and ask you, how many sodas did you drink today? They will say that, oh, I drank 2 today. So now they will measure your bone density. So this is like the number of soda. Then they will measure your bone density. Then they'll write it down. So this is like X, this is Y. So then they'll write, I don't know how it is measured by, if it is like 2.1, whatever, I don't know. They'll write it down. Then they will ask you the next day, how many sodas did you drink today? If you said 3, then they will measure your bone density again. And whatever it was, or this, they will write it down. Then the next day they'll come again. If you are increasing the number of soda you are drinking every day, I don't know how it's going to affect your bone density. But if we have that to be maybe 5.1, they will write this down. So it's just one individual. This individual, let's assume, is one of us, and they are asking us how much soda we drank. So you drank the soda, so you know how many.
I just had a quick question. As in terms, will you use explanatory or will you use predictor variable usually?
Yes, I will. I will.
The same thing.
I will explain that to you very soon. The explanatory and the predictor, I'll explain that to you very soon.
I mean, I'm saying like in problems and tests and stuff, will you use both of those words, or are you generally going to use explanatory variable or predictor variable? Which one?
We will use both.
Oh, use both? Okay.
Yes,
okay.
But I haven't talked about that yet, so I'll talk about it very soon. Yes, but we use it. So now they will measure that on you. So it's one individual, you are drinking the soda, so it's going to your body. And then at the same time, they want to know the bone density. So it's one individual, and we are getting this information from you, the individual. We all agree that if we are drinking the soda, then based on how much we are drinking the soda, if I don't know the relation between soda and bone density, but let's assume that the soda is decreasing your bone density. That is what I have written there is wrong. So if the more soda you take decreases your bone density, then it means that as you drink more soda, then your bone density is going to decrease. So the more soda you drink, the more your bone density decreases. So one depends on the other. So the bone density would not decrease if you had not drunk the soda. So if your bone density is decreasing because of the soda, then it means that this X that we see here, you see I've written it as X and Y, this is the number of soda you drank. So the more soda you're drinking, the more your bone density is decreasing. So in that case, this X is what we call the explanatory. That soda you drank is causing your bone density to decrease. So we call Y the response. So the body responded to the soda. Why? Because the soda that you drank, you knew that definitely is going to cause some change. And so because it's causing the change that is causing, it is responding, the body is responding to it. So y is usually called the response variable. What caused that change? It has to be explained by the soda. Because you drank more soda, that is why your body is decreasing. So the X is what we call explanatory. And apart from saying explanatory, we can also say predictor, because the X is predicting what is going to happen to your body. So it's like what we did in elementary algebra and intermediate. If you have y is equal to 2x plus maybe 4, if we put in our x value, we usually choose our own x value. Based on the x values, we are able to get y. So the y is a response. It's a response to what we are plugging in place of x. So always remember that in statistics, and especially in chapter 4, our response variable is your y. It's like that. Put in, and the response is that whatever you got is going to be your y. So y is the response variable. That response variable be explained by the value of x. If I put 0 here, then I'm going to get 4. If I decide to put 2 here, then I'm going to get y to be 8. So y is responding to the value here. So the x here is like explanatory. So some of the questions, it doesn't tell you which one is your x or y. By just reading and critically thinking about it, by using the illustration I just used. And whatever you give you two variables, whether that variable that was given is explanatory, that is x, or that variable that was given is your response. So explanatory has the letter x. So remember that explanatory is always the x variable. The x is like when you are plotting x and y, that is your x. Explanatory is also called predictor. So it can sometimes say explanatory, sometimes use the word predictor. So just remember, it can be used interchangeably, or it can be used at the same time. And what's the response? That is what is coming out. That's the result, the feedback. That is the response. Response is the value. Response is the variable whose value can be explained by the explanatory. So explanatory always explains changes in the variable. Response is the one that can be explained by the explanatory. So if we have our x and y, assuming we have our response, we have explanatory, we can draw what we call a scatter diagram. So sometimes you'll be given those values to, and the rest you have your x and then you have the y, and then you'll be asked to draw a scatter diagram, just like the name implies. Scatter diagram is a graph that shows the relationship between two quantitative variables. Because we are dealing with numbers, x and y values, we are dealing with quantitative. So it is relationship between quantitative variables measured on the same individual. It has to be the same individual. It cannot be James and then we choose another person. No, it has to be that same individual. Each individual in the data set is represented by a point. And when we say a point in math, which we all know, it means it consists of an x coordinate and then y coordinate. So x and y, it consists of the explanatory and the response. So each individual in the data set is represented by a point in the scatter diagram. The explanation is plotted on the horizontal, which we already know. If we have our Cartesian plane, our x is always going to be horizontal. That is explanatory. And then the response is your y, and that is on the vertical axis. So some of this we already know from high school and then elementary and intermediate. So let's draw a scatter diagram. So we have some information here. It says the data on the right are based on the study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which drilling begins is the explanatory variable x, and the time in minutes to drill 5 feet is the response. Draw a scatter diagram. So we are fortunate, it has still does that. We are looking at two variables. The variables are the time. We are drilling depth. Depth is the same as like height. It's going down. You are drilling a hole on. It is the height. We are talking about the height. So we are drilling a hole or just the rock, and then it is being considered. The height is being considered with the time. So we are looking at time. Time is one of the variables, and we are also looking at the depth. As you drill a hole or you drill a rock, you are looking at the height. As you drill, it goes down, so a height. So we are looking at height, and at the same time, we are looking at time. So those are our two variables, depth and time. So if you haven't dug any hole, or you haven't dug the rock or whatever it is, if you haven't dug it, then it means it is at a height of 0. You haven't done anything, just the bare floor. You haven't started digging it, so that is 0. Because you haven't done anything, the time is also 0. Now you decide to dig. So as you dig the hole, now you decide that you want to drill a hole of 35 feet. So the rock or the hole you are drilling, the height is 35. So as you drill, you start from 0. The beginning is 0, then you start drilling. As you drill it at a height of 35, it's taking time to do it. So the more the higher the height, or the more height or rock you are drilling, the more time it will take, because the time is dependent on the height. So if you decide to do 35, then now you have to start putting in your time, and then tell you how many minutes you used for the 35. So the time is dependent on the height. So the more drill you are drilling, or the hole you are drilling, the more or the higher the height, the more time it will take, because the time is dependent on the drill. It's dependent on the height of the drill. So this is considered our X. Our X, the drill doesn't depend on anything. You just decided to drill, you are drilling your hole, so you are just drilling a drill. But if you want to know the time that you used to drill, then you have to set your timer. So the time is dependent on the height. Because of that, explanatory or predictor is also called independent variable. It doesn't depend on anything, but the time here is dependent on the height. So the response is also called dependent. So response is dependent. The response, which is why it always depends on X. So here we are fortunate. It has already told us that height should be explanatory. Sometimes it will not tell you. If it doesn't tell you, then you have to sit down and think about it. Is my height depending on anything? No. The time is rather depending on the height. So in this case, the height, which is the same as the depth, is the explanatory. That is dependent. But the time, which depends on the height, is dependent. So that is the response variable. Now that we know that our depth is X and our time is Y, we can now go and draw our paradigm. This will be given to you. This information that we have here will be given. So we have our variable. So when it was done at 35 feet, the time that was used was 5.88. When we got to 120 feet, the time was 7.4 minutes. When it was 175 feet, the time it used was 7.6. So we realized that as the height was increasing from 35, you can see it's increasing. So as the time, the height here was increasing, we also realized that there was an increment in the time. So it wasn't like a regular increment, but there was here, we realized it increased from here to here. This also increased from here to here. Here it decreased. So it wasn't regular, it wasn't consistent. Some of them it was decreasing, but in general, realized that there was some sort of increment. So as this was increasing, this was also increasing. It wasn't a perfect increment, because some of the cases it decreased, like from here to here it decreased, even though we are increasing the height. So from this information, we can draw a scatter diagram. Scatter diagram are very easy. You have your X and Y. So you are just plotting points. So this is X, look for it corresponding Y, plot it as a point. So this is X, this is Y, this is X, this is Y, till you get to the end. So if we were to plot this, the question says that we should plot, let me say, So they didn't even say it here, but oh, okay, said it here. So draw a scatter diagram. So the question says that draw a scatter diagram of the data. So it has given us what information about what this data is, and now it wants us to draw the scatter diagram. Very simple. Take this and this. That is the x and y. X and y. So we just have to make sure that we have our scale. So time, which is y, and then x, which is the depth, is on the horizontal. So looking at the x, the smallest is 35 all the way to 190. So you can decide to use differences of 50-50 or 30-30, whatever you want as your scale, you use it. And then for the y, the smallest we have is 5.50. The highest we have, I think, is 7.97. So we are choosing between 6 and 8. So 6, 7, and 8. And then we just plug it. Take 35, which is going to be somewhere here. And then 5, 8, which is below 6. So that is your first point. The second one is 50 and 5.9. 5.99 will be a little below 6. And then this is 75. 75 will be between midway between 50 and 100. And it has 6.47. So 6.47 is below 7. So you do it for all of them. So you are doing it from the first point to the last point. And when I say a point, you have x and y, all the way to the end. So this is the scatter diagram which corresponds to this data. Then after drawing your scatter diagram, you just write a title here to show that this was drilling time versus depth. So y is your drilling time versus the depth. And that is it. So x goes on the horizontal, y goes on the vertical. That is how we draw scatter diagram, which is so easy to draw. After drawing your scatter diagram, relations in a scatter diagram. We have types of relations. Some of the relations that might come across is what we have. Depending on the data that we're given, you can get a scatter diagram which looks like this. So you can see that they are all moving in the same direction. Even though the one we did was all scattered around, these are moving in the same direction. If we were to even draw a straight line through it, it's possible to draw like a straight line through most of this point. So in situations where you have scatter diagram, where you can see that they are moving in the same direction. And again, from algebra, from left to right, you can see that this is increasing. If I were to draw like a line through some of this is going upward, it's increasing. When it is increasing, we can draw like a straight line. Because we can draw a straight line, we can think of this as linear. There was no straight line, but based on this, we can imagine that this is linear. So this is linear. From left to right, if we were doing it, we realize that it's increasing. And in algebra, if it's increasing, it means it has a positive slope, or there is a positive relation between them. But the scatter diagram, we just want you to just show whether it is linear or not. Later on, come across the positive slope and the rest. But for now, we just want the linear. So you can see it's linear. They are moving the same direction. This direction would have been a positive direction. So set cases where we have positive direction, it means that as the x was increasing, y was also increasing. They both had some sort of increment. They were all increasing at the same time. This one also seems to be linear. We can draw like a straight line through some of these points. Or if we draw a straight line between here, some of them will lie just directly around the straight line. This is also considered linear, but this is a different direction. From left to right, if we start from left, this is going down, it is decreasing, it is falling. So this would have been a line which will have a negative slope. And when we have negative slope, it means that as one of the variables was increasing, the other was decreasing. It's like when I was using the soda and the bone density. If what I'm thinking is true, then it means that the more soda you drink, the less your bone density. So as one is increasing, one is decreasing. That will give us a negative slope. So for now, we just want to know whether it's going to be linear or not. You can see that because it's like in the form of a linear. Linear means a line. You can draw a straight line through it. This can also have like a straight line. Let's look at C. If after drawing your scalar diagram, this is quite clear now. Straight away, you know that this is not going to be a straight line. This will look like parabola. Those of you who do the x squared plus 3 and the rest. This is like a parabola. And parabola this or like that. So this is not a straight line. So in this case, this is not linear. It's not linear. And then we also have this. If your scalar diagram came out like this, you straight away you know that this is not linear. So not linear. And don't have relation. They have relation, except that the relation is not linear. This is not linear. This is not linear. And here it says that no relation. So in this case, we realize that we have this. So when they have no relation, it's possible that as x was increasing, the y values remained the same. It did not change. So they didn't really have a relation. Here, when we have this, it's possible that it looks like this. So here our y squared would be like positive. And here they had a relation, just that it wasn't linear. So if you come across questions like this, where it actually is this linear or non-linear, it's very easy to answer this. This is linear, this is linear, this is non-linear, this is non-linear. Here they didn't have any relation because this is not linear. So one of the variables remained the same. It was constant, stagnant, while the other was increasing. So that is about different types of scalar diagrams that you might come across. So sometimes we'll be asked to interpret a scalar diagram. So two variables are linearly related. So two variables that are linearly related are positively associated. That is, we have like a positive slope. When above averages of one variable are associated with above average values of the other, or when below averages of one variable are associated with below averages values of the other. In short, what this means is that two variables are positively associated. If as the value of one increases, the other increases. If x is increasing and y is also increasing, then we should get a positively associated diagram. Or if as one decreases, the other is also decreasing. So if they are both increasing or they are both decreasing, then we get a positive association. So they both have to increase or they both have to decrease. They have to be the same in order to get a positive association. An example of that is this: they are all going in the same direction. So if they are all increasing or decreasing at the same time, then it's positively associated. If they are negatively associated, then it means that as the value of one increases, the other decreases. That means one has high values, the other has low values. So as one increases and the other is decreasing, then we are going to have them to be negatively associated. That means they will have like a negative slope. And we also have what we call linear correlation coefficient. Just the scalar diagram alone can give you information, but it doesn't give a lot of information. It just tells us this is linear, that is, it doesn't tell us the value of what the linearity is. Like if you have a straight line in math, if you have your straight line as 2x, and look at this and see that this is my slope, this is the y-intercept. So we have some numbers associated with diagrams. Just tell us this is linear, this is linear, this is no relation. If we want to start making sense of it, and then also to see what we call the correlation coefficient, then we can look at how to describe the properties of linear correlation coefficient. When we say linear correlation coefficient, it tells us about the strength and direction of the linear relation. So we have seen that the first two is a linear, so it's a line, and this is also a line. But if you want to know the strength of this line, if you want to know the direction, you can look at this and see that this is positive. So positive is the direction. But if you really want to solve something or work around it to see the positiveness and also to see the strength of it, then we consider what we call the linear correlation coefficient. So linear correlation coefficient is also called Pearson product moment correlation coefficient. But just remember the first one. It is a measure of the strength and direction of the linear relation between the two quantitative variables. We have the population correlation coefficient and the sample correlation coefficient. The population has this symbol which we call rho. It's like a P which has been itemized, and the sample correlation coefficient is R, small r. For the purpose of this class, because it's elementary algebra class, we only consider the small r. Small r is the sample correlation coefficient. And this is the formula for sample correlation coefficient. If you want to know if your straight line that you have, want to know the strength of it, then we have to find r. R is a number which is between -1 and 1. So inclusive. It can be -1, it can be +1, or it can be any number 1. So if we have -1, then it means that the values on that line, so if we draw a line, it means that if it's negative, then it means from left to right it is falling. So it means that the values here are going to be on a perfect straight line if your r is negative. So you haven't drawn your scatter diagram, but you have been able to solve for r straight away. If your r is -1, that means they will all lie on a perfect straight line. The values will be perfectly lined up on a straight line, and it's going to have a negative slope, left to right, left to right. This is falling, it's going down, it's decreasing. If you have +1, then it means that if you had drawn your scatter diagram, the point would have lied on a straight line, which is positive. From left to right is increasing and it's perfect. So when the values are getting close to -1, it means we have strong correlation. If the values are getting close to positive, we still have strong correlation. But this should be positive correlation, this should be negative correlation. And they all depends on the value of R. So this is how we solve R. This is the formula. So from the formula, we've seen our notation X bar, which means we have to find the mean of all the X and then subtract each of the data value from the mean. And then we will divide it by the standard deviation of the X variable. Then we come to the Y, we do the same. Find the mean of the Y, subtract each of the Y values, and then subtract the mean of each of the Y values. Then we divide it by the standard deviation of Y. Then you can see they are multiplying. So we will multiply, and then after that, we will add all of them, add all the products. The last step is to divide by n-1. What is the formula for linear correlation? Don't worry, those of us who have the calculators, when we get to 4.2, then I will show you how you can use the calculator to calculate R. But for 4.1, we are going to do it by hand. 4.2, I will show you how we use the calculator to calculate R. Where X bar is the mean of the explanatory, S subscript X is the standard deviation of the X variable, Y bar is the mean of the Y, and then S subscript Y is the standard deviation of the Y. And N here is the number of individuals in the sample. So this is how we calculate R, and R is the one that tells us the strength and direction of the line, strength and direction. So the properties which I've already mentioned, one is R should always be a number between -1 and 1, or it can be -1, or it can be +1. So between -1 and 1 inclusive. Inclusive means it can be -1. That's why you see the equal sign here, or it can be +1, or any number between them. If your R, after calculating it, you get a +1, then it means we call it perfect positive, and certainly so if you are getting that end point to be 1, exactly 1, then that's perfect. And because it's positive, perfect positive linear relation exists between the two variables. If you are getting it to be -1, then minus, this is like the beginning point. That is the perfect, not so perfect, but this is negative. So that will be perfect negative linear relation. It exists between the two variables. So it means that here, as they were both, as one was increasing, the other was also increasing. As one was decreasing, the other was decreasing. And here it means that as one was decreasing, the other was also increasing. So vice versa. Here they are both increasing, or they are both decreasing. Here, as one was increasing, the other was decreasing in the same manner. If you don't get exactly positive one, but it is close to positive one, like if you are getting 0.9 or 0.99999, this is very close to saying one. So that means we use the word stronger. We say that if R is, the closer R is to positive one, the stronger the evidence of a positive association between the two. If it's getting close to positive one, there is a stronger association of a positive correlation. And then if it is getting to negative one, very close to negative one, like negative 0.99999, we say that the stronger the evidence of a negative association between the two variables. So these are just properties of the linear correlation. And if R is 0, just imagine R has to be between -1 and 1. And if R is 0, so this is the number line, this is 0, this is -1, and then this is 1. These are the values that R can take. So if R is 0, then it means it's in the middle. Then it means that there is little or no evidence of linear relation. Because as it gets close to -1, then it means there is a strong negative association. As it gets close to positive one, there is a strong positive association. But if it is in the middle, then there is little or no evidence of linear relation. That means that it was like the one which said it is like this. If it's like this, there is no linear relation. Or if it is like that, no linear relation. In that case, their values will be 0 or getting close to 0. The linear correlation coefficient is unitless. It's not measured in feet or meters, no, it's unitless. So the unit of x and y plays no role in the interpretation of R. Linear correlation is not resistant. So can somebody explain this? We came across not resistant and resistant. Say that linear correlation is not resistant. Do you remember resistance? Do you remember what we said about resistance? If it's not resistant, then what does that mean? Anybody want to
Means to
help us?
resist or push against.
Great, thank you so much. So since it's not resistant, then it means that it can easily be pushed against. Yes. So thank you so much. So when we did that in chapter 3, we realized that when it came to the mean and the median, the mean was not resistant. It wasn't. It was easily affected. It was easily pushed against. So the same applies here. Coefficient is not resistant. But we realized that for the median, it was resistant. It wasn't easily pushed against. It wasn't easily affected. So median is resistant. And just realize that correlation coefficient is like the mean. It is not resistant. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation. So as soon as there is an outlier, it will easily affect the value of the linear correlation coefficient. So that is some properties about the linear correlation coefficient, which we should remember. If you forget any of this, please don't forget the first one. The first one says that R has to be between -1 and 1. This will always be the values of R. So if we have noticed that there is a linear relation, then if we were to find our R from our calculator and we realize that our R is +1, and then we go ahead and decide that since we know it's +1, let's draw a diagram, let's draw a scatter diagram to see how it will look like. Then your scatter diagram is going to look like this, because you are saying that your R is +1, is perfect. So this is perfect. I'm not good at drawing, but I know that if I were to draw the line here, straight line because all the points are nicely lined up. This is what we call positive linear relation. And from left to right, we can see it is going up. So when r is equal to 1, then that means we have this is positive 1. So we have a perfect positive linear relation. So linear correlation, it tells us the direction and the strength. So the direction here is that it is going upward, and the strength of it is positive. So R is equal to positive 1. And then here, if we were to take our time and to draw a line through it, we know that most of these points of them will lie on a straight line. It is not exactly 1, but if we were to draw lines, some of them will lie on a straight line and others will be outside of the line. This is what we call strong positive linear relation. This will have R, which is approximately 0.9. On the number line, we know that 0.9 is getting a little close to 1, so we use the word strong. If it's exactly 1, we use the word perfect. If it's getting close to 1, we say strong positive linear relation. This is positive 0.9, so positive. And when we look at this, you can see that they are all scattered around. If I were to draw a line here, because they are all scattered, I don't know whether to draw it going this way or to come that way. So we still have some sort of linear relation here. But as you can see, majority of them are like scattered around. I don't know whether to try here or that here. This will have R, which should be approximately 0.4. And if you have 0.4, then that is moderate. So it's like between 0 and 1, not even exactly in the middle. Moderate. This is moderate positive linear. And why is it positive? Positive, still positive, because from left to right, it will increase. It doesn't matter whether you draw it here or here or there or that, it is still increasing, so it's positive. Now let's come to the negative. Negative is when you have left to right and you realize it is falling or it is decreasing. So again, looking from left to right, you can say that this is from left, and then if I were to draw that line, oh, I couldn't draw it to pass through. I thought it was going to pass through, but assuming we have drawn the line and it passed through it perfectly, it would have been perfect because we have all these points, so a perfect straight line, and they'll all pass through this point. But from left to right, it is falling. If it's falling, then that is negative. So this is perfect, and because it's negative, our R is -1. -1. And from here, we can see that we can still draw a straight line. It will pass through some of these points in a straight line, just others will be like on the side of the line. R here is approximately -0.9. So this is strong negative linear relation. Here they are scattered around. If I were to draw my line, I can decide, should I draw it here or go here or that way? I can still draw a line through some of this, but majority will be outside of the line. And our R would have been approximately -0.4, which means that this one is moderate negative linear relation. It doesn't matter where I decide to draw my line. From left to right, it will still be falling. It will be decreasing, so it's negative. If we look at this and we draw a line, if we were to draw a line, you can decide, let me go this way or let me go that way. So you don't know whether to go that way or that way. Even by looking at this, somebody can also decide to do something like that. If this is a case where we are getting our R close to 0, not linear relation, because if we were to draw it out or down, then you don't know whether it's left or right, because you can go that way, you can go that way, you can even draw a curve. So this is no linear relation. R is close to 0. And here we have this, which straight away shows that it looks like a parabola. And if it's like a parabola, then that is not linear. So in this case, no linear relation. R is close to 0. So as part of your homework, some of the questions you get these diagrams, and then you also have like the R's written somewhere. And then if you get like a diagram like this, it will ask you, do you think that this is R equal to 1? So it will give you some R values, like R is 1, to give you R like 0.9, like we have here. It to give you r which is 0. So assuming these are positive, let's use the positive one. Assuming you have been given these diagrams without this, you have been given that diagram, and you have this separated somewhere, written somewhere, you asked to match them. Then because you see that this is perfect, then you match this with this because perfect correlation. Then since this is 0.9, you see that has like a strong correlation. Match this with this, and since you see that this is like all scattered around, then that will be the moderate. So you are just matching the diagrams with the corresponding values which were given to you. So those are some of the questions that you might come across on your homework. So now let's find our R. Remember we came across R. R has to be a number which is between this. If you are getting 2 as your R, if you are getting an answer of R which is 2, straight away you know that is wrong. R cannot be more than positive 1. It cannot be less than negative 1. It has to be a number between here. So we are going to look for the value of R. We are doing it by hand in 4.2. When we get to 4.2, I will show you how we use the calculator to find R. And the PowerPoint for 4.2 is also up. In that PowerPoint, it tells you the steps for finding what we call least square regression line. As part of those steps, R can be found in those steps. So we are going to find the linear correlation coefficient of the drilling data below. So this is the same data we came across. This time we are doing it by hand because I haven't shown you how to use data yet. This is the formula we came across for the correlation coefficient. We are using the one for the sample. So is this one divided by n minus 1. So summation, then we have x bar, x minus x bar divided by the standard deviation, which is multiplied by, I don't have enough space, so multiplied by y, then we have the mean, and then the standard deviation of y, and everything divided by n minus 1. This formula we are using, so is this that we have here divided by n minus 1. Since we have only been given x, and then we have y, and we can see from the formula that we need the mean of x, we need the mean of y. In our calculator, we can put this in to get the mean of x, put in to get the mean of y. Then as you get the mean of x, it also gives you the standard deviation. You know it's the same process. Those of us who are using the TI, it's the same process. That process will give you your mean, and at the same time gives you your standard deviation. So put in the values and it will give you your x. Get the x bar, write it down. Get a standard deviation, write it down. Then we'll do the same for y. Put in the values for y. Get the mean and get the standard deviation. Now, if we know the mean, which I've summarized here, the mean of x is going to be 1.26.25. The standard deviation will be this. And then for the mean of y, we are getting this, and its standard deviation is what we have. From the formula, we can see that it says this is a parenthesis. So we do what is in the parenthesis here. What does it say? It says that we should take each of the x and subtract the mean from it. So this is your mean. So you're going to subtract your mean. I don't have enough space, so I'm just writing it as 126 minus 126.25. We're subtracting the mean from each of these. So you get to the end. As soon as you finish subtracting, so this subtracted from, just divide it straight away by the 52. So subtract the mean from the x, divide it straight away by the standard deviation. That will give you this. So subtract the mean again from our x, divide it straight away by the standard deviation. That will give you that. You are doing it for each of these. So for each of these, you subtract the mean. As soon as you subtract, divide it straight away by the standard deviation. Do it for all of this. The second part of the formula says we should do the same for y. So we look for the mean of y, 66.9. Then we take each of the values of the y, and then we subtract 6.98 from it. So subtract. Use as many decimal places as possible. In your calculations here, you can see this has a lot of decimal places, about 4 or 5. So take this mean, subtract it from each of these data values. So we get to the end. And as soon as you subtract, let's divide by the standard deviation. So as you subtract this, whatever answer you get, straight away divide by the standard deviation that you do with it. Whatever answer you get, 5.999, subtract the mean from it, you divide it straight away by the standard deviation. You do it for each of them. That gives you this. That is what this part of the formula tells us. Take the mean, subtract from the data, and divide by standard deviation. After that, if you are looking at our formula here, our formula says that after you have gotten this, which is in parentheses, and you have gotten that which is in parentheses, multiply. You don't see additional, subtraction, or division here. It's simply a multiply. So you take this answer you got there, multiply by this times this. So each of these, that is column 3 and column 4, you are just multiplying to give you this product. So when we multiply to give us this, we take this, multiply by this, you do this, take this, multiply to give you that. After you are done with that, just go ahead and then add. So we add all the values in this column. So this was the first part of the formula. This is the second part of the formula. You can see we are multiplying. So because it's multiplying, we multiplied all these. We got this product. After getting this product, add all of them. That gives us this. And the last part of the formula says we should divide by n minus 1. So what is n? So for n, please don't think of this as this is 1, and this is 2, this is 3, this is 4. For your n, remember the aim of doing this is we are measuring this on the same individual. So this is considered as 1. The 1 is for both of them. This is considered 2 for both of them. So we are counting. So this is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So just count how many. This is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 12, not 24. Don't think that because this is X and this is Y, this is 12 and 12. No, it's just 12, not 24. So our n here is 12. So as part of the formula, divide by n minus 1. So 12 minus 1 would be 11. And when we multiply this, we got that. So whatever, after multiplying and adding, you got that. So whatever you got as your numerator, divided by 11, and that's a good unit. So that is what we're going to do. This is a lot of work. Some of it, I will start on the calculator. I was going to show you in 4.2, but I'll try to see if I can show you before we even go to 4.2. So that is how we calculate R. The formula is what we have to get your mean, subtract each of the data values from the mean, divided by the standard. So as you subtract, just divide straight away. As you subtract, divide straight away. Then you come to another column, take the mean of 1, subtract it from each of the data values. As you subtract, divide. As you subtract, divide. So you have this column, you have that column. You can see that it's multiplying. So multiply straight away. And then you add the product. So whatever you got from multiplication, add each of them. And that will give you the answer for the numerator. For denominator, you are counting how many you had. In this case, you are counting how many you had. In this case, we had 12 of them. So 12 minus 1 is 11. And then you just divide. So that is how we find R. So after you have gotten your R, sometimes we'll be asked to test we'll be asked to do some tests, and that test is to determine whether a linear relation exists between the two variables. So we are going to test for linear relation. The R that we came was just telling us the direction and the strength. And we are testing for linear relation. So to test for linear relation, we need our R. R is important. So if the question asks you test whether a linear relation between two variables, then in that case we have to know our R first. So I will show you how to do the R on the calculator so that we don't waste time to do all that calculation if you don't want to. So I'll show you the calculator before we look today. But if it wants the linear relation between two variables, then we have to test for that linear relation. To do that, our first step is to find R. It doesn't matter if you're getting negative or positive R. just look for the absolute value. We know absolute value from elementary algebra in case you've forgotten elementary intermediate. If you have a value like negative 2.85 and you're asked to find absolute value of that, means you are just putting this two vertical lines here. If they are negative, it just becomes positive. So absolute value of negative 0.85 is positive 0.85. Any negative value, when you find its absolute value, it becomes positive of that number. If it's already positive, then just leave it as positive. But if it is negative, the absolute becomes the positive. So look for the absolute value of your R. So assuming you have already done the R, what is the absolute value of the R? Then we will use a small table which will be given to you in the question. If this question is being asked, you will be given a critical value table. An example, part of the table is what I have here. This table is a long one, but this is part of it. So you'll be given this table. We call it a critical value table. Then you consider your R, which you had already solved. If the absolute value of your R is greater than the value from the table, then we will say that a linear relation exists between the two variables. So if if the absolute value of R is greater than critical value, then we say that a linear relation exists. Let's look at an example. We just did this example and we got our R. So when we did our example, which we just did, we got our R to be 0.773, which is already positive. So our R, which we just did, we have our R to be 0.773. As part of the steps I just read to you, you have to take absolute value. This is already positive, so its absolute value is still positive. So 773. This is our R. Now we go to our table here. We are going to look for the critical value corresponding to N, which is equal to 12. Our N is 12. So go to N here, look down all the way to 12, and then look for the value corresponding to 12. So our critical value, which I'm writing it as CV, our critical value here is 0.576. This table will be given to you. Don't memorize it, it's given to you. So our critical value is 0.576. If our R, which we solve, is bigger or greater than the critical value, then it means that a linear relation exists between the two variables. So since our R is 0.773 and our critical value here is 0.576, and we know that this is bigger than this, then it means there is a positive linear relation between the two. So since this is our R and is greater than the critical value, there is a positive linear relation between the two. And why did I use the word positive? I used positive because our R was positive. And I just realized that there is a linear relation. The critical value tells you whether there is a linear relation or not. Because remember that some of the scatter diagram that we drew, some of them did not have any linear relation. Now this is telling us that there is a linear relation. So to determine whether there really is a linear relation between them, then we have to get our R, and then based on R, which we got as 773, we look for our N. N is 12. Go to this table, look for 12, and then what is the value corresponding? That is this. Since your R is bigger, absolute value of R is bigger than this, then it means that there is a linear relation between. And since your R was originally positive, then we see a positive linear relation. So that is how there is a linear relation. So if actually there is a linear relation, then we know from intermediate algebra that if we have a linear relation, then we should be able to find the equation of that line. Linear means there is a line. So if there is a line, then what is the equation of that line? And that is what we are going to do in 4.2. In 4.2, we are revisiting what we know from elementary. We are looking at equation of a line. Because now we have determined that there's a linear regression, so we have to know the equation of that line. And if you are looking for equation of a line, you have to know your slope and y-intercept and the rest. So this brings us to the end of 4.1. Before we leave, I was going to show you how to find R in 4.2. But before we go to 4.2, let me show you how you can find R, using the TI-8384. The steps in finding R is in 4.2. So let me bring up 4.2. I'll show you the steps of how to find R. So this is 4.2 is already on Canvas. You can look at it later on. And let me just go straight away how you can find R. So this is what we'll be using to find R. To find R and also to find what we'll be doing in 4.2. The steps are we are going to put all the X values in L1. You already know where to locate L1. You go to start, edit, under edit, you see L1. And then we put X values in L1. We put X values and Y values in L2. Then we will turn on what we call diagnostic. And to turn on your diagnostic, you have to select second function and 0, second function and 0. Then we scroll down all the way to diagnostic, and then we press enter twice. And then from the home screen, we go to start again, then we calculate. This time we select this. If you select this to give you the value of R, and it will also give you this, which will learn in 4.2. So let me bring up the calculator, and then I'm going to show you how to find R, so that if you start doing your homework for 4.1 and you want to do all the calculation I showed you, you can just follow these steps, and based on these steps, it will give you the value for R. So let's go. Let me assume that the calculator is off, and then let me turn it on. So I am going to follow these same steps that we see here. And then we are going to find the value for R. So your first step is putting the values of X in L1 and putting the values of Y in L2. Let me bring those values that we did in 4.1. We want to find R, which we just calculated in 4.1. These were the values we were using in 4.1. So I'm going to use those same values. These were the values we were using in 4.1. So I've read the steps to you. We are following those same steps. So I'm going to bring the calculator up one more time. So this is our calculator. This is our calculator. I think you should be able to see on the screen. Let's see. Did you all see the calculator on the screen? Please let me know if you see it. Did you see the calculator on the screen? Okay, yes. Great. Thank you. So now, thank you. So on this calculator, we are going to put in all these values under L1, and all of this will go under L2. So we turn our calculator on. Now we go to start. We know that to put this in the calculator, we have to go to start. Under start, we go to edit. So we choose edit. And then under edit, we are going to put in all these values. And I know that you know how to put in the values because of time. This is a lot of values. I don't even have a lot of time to teach. I wish we had more time. I only have 6 weeks. So because of time, I put in the values already for you. So this is our 35, 50, all the way to 190. So these are the values that we have here for our X. Then we have to put in values for Y. This time we have X and Y. So to get to your Y, you use this arrow to take you to the second column. And then on the second column, you are putting your values. So if there's anyone here who still don't know how to give values, just wait up the class out. So we are putting in the values for Y. We are putting it under L2. So we go to 5.88, we put it in 5.9, and we put in all the values for Y. So we get to the end. So the last one is 7.9. After putting in all these values, this time you want R, and in 4.2 you are looking at what we call the least square regression line. So we are looking for R, and at the same time, we want the least square regression line. So after this, from what I read to you, your next step is to choose this. We choose second function, which is the yellow one, and then we choose 0. That will bring what we call catalog. So press second function and 0. That brings up catalog. Those are the steps I read in 4.2. So catalog. And the catalog, we want diagnostic on, diagnostic. So diagnostic starts with a D. You can see that these are all in alphabetical order. So on the keyboard on your computer, you can click on D. So when you click on D, all the D starts showing up. And you want to go all the way to diagnostic. So you can use this downward arrow to go to diagnostic. We want diagnostic to be on. So we press enter twice. So 1, 2, and then it will tell you that the diagnostic is on. So after you've realized that the diagnostic is on, now you go to start. So this time you go to start, and we want to calculate. So you go to calculate. And in this calculation, we are not using the usual one we have been using so far. We go all the way to 4. These are all steps on 4.2. I just read it to you. So we go all the way to 4. So you can use this downward arrow to go all the way to 4, or you can click 4 straight away, and then press enter. And then because we are using L1, L2, we are going to put L1 and L2. So you go to second function, L1, and I'll look for the YouTube video on this for you in case you still don't get it. You can watch those YouTube video. I'll check to see if YouTube has it. Obviously, they might have it. And then we go to second function, L2, and then enter, and it summarizes everything for you. Remember when we did our R, we got that to be 0.773. That is what we see here. That is our R. So we are getting our R to be 0.772. So if you don't want to do all of this calculation, then you have to use the steps I showed you, which is 0.7228 and the rest. So you can use these steps I showed you if you don't want to do this. So that is your R. In 4.2, I'll be showing you the rest. The rest, you don't have to worry about those now. That is why I didn't want to even show you those till we got 4.2. But I realize some of you might be doing your homework ahead of time. So this last one is your R, which is 0.77282. And that is exactly what we got here. We got 0.772, which we have rounded it to 3 decimal places. So this is asking, this covered in the calculator instructions. No, just I don't think I've given you any calculator instructions. So Jesse, which calculator instructions are you referring to?
I might be getting this mixed up with another class, but I thought that I saw something from you that was like instructions on how to use a calculator for different formulas. I might be mixing this up with a different class. I'm in a university stats class too, so it might be that one.
Oh, okay. Oh, okay, that's fine. Oh, you are taking university stats class?
Yeah, University of Redlands. Yeah.
You are?
Yeah.
Okay, great. Oh, I used to teach that too. Okay.
Thank you.
No, then you are ahead of us. That is great. So, and what I put on Canvas was rather the link to watch a YouTube video on how to use the calculator to find the mean, the median, and standard deviation. But after class, I will look for the YouTube video that goes with this so that you can also watch that. But I'm going to go over the steps again. So Jesse, thanks for that. I'm going to go over the steps again. So the steps I'm using was, let me bring the calculator. You can see the calculator. So the steps I used was obviously to put in our L1, L2, because we had our X values, Y values. So I first went to start, and then under start, I chose edit. So edit is 1. And then after choosing edit, I put in the values for X under L1, which by now, if you don't know, please wait after class, I'll show you. So put in the values for all the X here. Then use this arrow to take you to the right, and then put in the values for the Y here. So after putting all these values, now this time, we are not going to go to start straight away like we used to do. This time we are in a different part of statistics. So we are using what we call diagnostic. So to get the diagnostic, we have to use second function and then 0. That will bring up catalog. So second function is 0. That brings up catalog. And the catalog, we are looking for diagnostic. It starts with a D. These are all alphabetically arranged. It's a lot of them. So in order not to waste time, go to your computer. On your computer, press D, the letter D. It will take you to the D's that we have here. Even under the D, we are looking for diagnostic. This is still arranged alphabetical. So we go all the way till we see diagnostic on. So that is what we see here. And then we press that twice. We press enter twice. So 1, 2, and then it will say diagnostic on, done. Then the next step is to go to start. And under start, this time we want to calculate. But the calculation we want is not the median, the mean, like we already know. This time we want the fourth one, which I'm going to show you 4.2. So go to 4. So you can choose 4 from here straight away, or you can use your arrow down all the way to 4. And then you press enter. And it summarizes everything for you. So far, what we've learned is this R. So it has given us the value R. Before to learn about, like in the form of equation of a line, to give us this information. So I will put the YouTube link on the report. If they have one over the same step, or better still, you can use the steps I have put on 4.2. So this is 4.2 on slide. So that should be this is slide 10. So for you, that should be slide 9. On slide 9, it shows you how to use the TI-84 plus to find correlation coefficient. That is what we see here. That's the same step I used. So I put the values in L1 and the Y values in L2. I turn on diagnostic by selecting second function 0. I scrolled all the way to diagnostic and I hit the enter twice. And then I went to start, I went to calculate and I chose 4 and I pressed enter. And then it gave me the answers. So even if you decide not to bring the L1, L2, it will still give you the same answer. So the first one I showed, I wrote L1, L2. The second I just showed, I didn't bring the L1, L2. It still gives you the same answer. But just follow these steps and I'll put it on Canvas if I find one on YouTube. Before we leave, let me briefly introduce you to this is already on Canvas. This PowerPoint 4.2 is what we call the least regression line. The least square regression, or we also call it the least square regression line. Least square regression. So because it's a lot of words, sometimes we just say LSR or the least square regression line. So as we were ending 4.1, we realized that there was a linear relation between our variables. If there is a linear relation, then we have to be able to know the equation of the line. So in this section, we are looking at equation of a line. Based on equation of a line, we look at what we call the least square regression. So our learning objectives will be to find the least square regression line and also to use the line to make predictions. Then we will interpret what is meant by the slope and also what is meant by the y-intercept of the least square regression line. Before we dive deeper into the least square regression line, we have to remind ourselves of how to find equation of the line in math, in algebra, if you want to find equation of the line. Does anybody remember the formula for any of the equation of the line? The equation of the line is, or the formula we use to find equation of the line. Does anybody remember?
Y equals mx plus b.
Perfect, great, thank you so much. So this is equation of the
I don't know
line.
how I remember that.
Yes, I'm glad you did. That is great. You know, I know it's been a while. It's been a lot of years for some of you since you were glad you remember. So this is why it's called mx plus b. This is the slope. This is the y-intercept. Another one is also y minus y1 is equal to m, and we have x minus x1. This is also another way of finding the equation of the line. And even after you have used this to find the equation of your line, your answer has to be in this form. It has to be in the slope as a form. So we can straight away use this to find equation of a line, or we can use this to find equation of a line, but we have to make sure that our final answer is in this form. As you can see, both of these formulas involve m. M is your slope. Does anybody also remember the formula for slope? Because we need all of this lesson. Finding your slope, which is m. Does anybody remember the formula? James, you want to try it again? I'm just kidding. So does anybody remember the formula?
I forgot.
You forgot that, right? Okay, you did great. I know it's been a lot of years. It's why so before we can even use this formula or use the second formula, we have to find m, because m is part of the formula. M is the formula given in size around from you have to so we know that you have x1, you have x. You can call this x1, y1. If these are x1, y1, then this would be x2, y2. The value for y2 subtract the 2 and the 1, but this has to be y. So y you have chosen y2, then this has to be x2. If this is y1, x1, this y1. This is, and that is, oh, you will get the slope. Oh, I'm cutting off again. Oh, sorry. So let me see what is going on. Hotspot is open. So the hotspot is still connected. Sorry, I don't know why I cut off again. I'm so sorry. So we have this as the formula. We can also use this. If you use the second one, the final answer has to be in this form. They both involve n, and this is the formula for n. Change in the y divided by change in x. You can name these values your ones, and this is your twos. If you are saying this is x1, then this should be y1. If this is x2, this should be y2. If you are using your y2 here, then directly below it should be x2. If this is y1, directly below it should be x1. So we are going to use all this information which we know from intermediate and elementary and high school to find equation of a line. So that is what we are going to do next. We are going to find of a line. So we are given this data. It says using the following sample data, find an equation. So what we are doing is we are finding an equation of a line that linearly relates data. We have seen that in 4.1 there was a linear relation. How do we determine the equation of that line? So that is what we are doing. We are using this as a sample data. So this is a sample data. We are asked to find a linear equation that relates x, x is explanatory, and that relates y, which is the response, by selecting 2 points from here and finding the equation of the line that contains these 2 points. You can decide to choose any point from here that you want. But if you want my advice, sometimes on my lab to tell you which specific 2 points to use. But if it doesn't tell you and you want my advice is that first draw a scatter diagram. After drawing your scatter diagram using all of these points, look for 2 points which you lie on a straight line or the line on that straight line. So draw your scatter diagram. If you were to draw a scatter diagram, in the scatter diagram, yes, the scatter diagram should look like this. These are the scatter. Forget about the line for now. Just look at the point, the scatter diagram. So your scatter diagram will look like this. Just the points, the square you see here is the scatter diagram. After drawing the scatter, try and sketch a line just in your mind, or you can sketch a line to look for 2 points that lie directly on the scatter diagram. So if you have drawn a line, look for 2 points that lies directly on the line of the scatter diagram. If you're not able to get exactly 2 points lying on the line, look for 2 points which lie close to the line that you have drawn. If on my math lab it doesn't tell that, use this point or that point, and it just says find the equation of a line. To find the equation of a line, you need 2 points. You need x1, you need x2, y2, which is another point. If it doesn't give you those 2 points, and it just said draw equation of the line, find equation of the line, draw a scatter diagram. After drawing your scatter diagram, try and sketch a line. As you sketch a line, look for 2 points that lie on the line. If you don't get 2 points that lie directly on the line, then look for 2 points that will lie close to that line and use those 2 points. So in my case, at home, you can try and sketch the scatter diagram. You realize that if you have drawn a line through it, these 2 points would have lying close to that line. We call them the best fits. So these 2 points which I've chosen here, that is 257, 2 and 5.7, and then we have 6 and 1.9. They would have lying on a straight line. If it's not on it, very close to that straight line. We are asked to find a linear equation that relates x and y by selecting 2 points and finding the equation of the line containing the point. So like I said, draw your scatter line, look for those 2 points close to the line or directly on the line, because we need 2 points. That is why it specifically say by selecting 2 points. So the 2 points I selected, which would have been on a straight line, is 2 and 5.7, and then we have 6 and 1.9. So this 2 and 5.7 and 6 and 1.9, we are going to use this to find the equation of a line. Just like our friend rightly told us, we can use y, which is equal to mx plus b, or we can use this straight away. But if you are using this, our final answer should look like this. So I'm going to use these 2 points, but as you can see, both involves m. So we have to be able to find our m. And m is what I wrote the formula down for you. So I'm going on a new slide, and I'll do this from the scratch and explain to you, because I know it's been a while since some of you were in an algebra class. So we are going to find the equation of the line, but before we find the equation of the line, the point I'm using are 2 and 5.7 as the first point, and then we have 6 and then 1.9. So this was x, always the first value is x, this is y, this is x, this is y. But because they are both x, y, we have to be able to differentiate between them. So this will be my x1, y1, this will be x2, y2. Now we are going to find slope. Slope is given as y2 minus y1 over x2 minus x1. Like I said, you can decide to make it y1 minus y2, and that should be x1 minus x2. So in this case, this is my y2, so I write that first. That'll be 1.9. I bring my minus, this is y1, and y1 here is 5.7, so I bring 5.7. Then I bring my division bar, and then here we have x2. So I go and look for x2, which I've written here as 6. I bring my minus sign. Then we have x1. So x1 here is 2. So I write. So straight away, my denominator I know give me before those who have calculated. You realize that your numerator will give you negative 3.8. So now we have negative 3.8, which we are dividing by 4, and that will give us approximately a slope of negative 0.95. So this is our slope. We did all of this just to get our slope. If you have your slope, which we shouldn't forget is 0.95, because I'm going to erase this soon. Our slope is, our slope is negative 0.95. Now that we know our slope, we can use the formula that James told us, which is this, or we can use this. Any of this will give us the same answer. The most important thing was for us to know our slope, and we have it. So we can now use any of this to find our equation of the line. I'm going to show you how you can use this and how you can use that to find equation of the line. And I'll show you how we can use it. I'm going to show you how to use the y minus y1 first. So we are using y minus y1, which is equal to mx minus x1. We know our slope, so straight away we just substitute our slope here in place of m. And then here we have y, so that will still stay as y. But here it says with y1, you can use any of this. You can decide to use this or use that in place of the y1 and x1. You can decide that you want to go with this, or you can decide that you want to go with that. So because I've already named this as the ones, I'm going to use this. If you try this at home using this, you get the same answer. So I'm using this in place of y1. I'm going to put 5.7. So I bring 5.7, and then this x is just x, so I bring it down as x. In place of x1, I'm going to put my 2. That is 2. And then from here, you just do your following, or you are just distributing. So when we distribute 0.95, which is negative on x, it means we are multiplying. So that will give us negative 0.95. And then when we multiply this by that, negative and negative becomes positive. And when you multiply this by that, you get 1.9. On this side, I'm left with y minus 5.7. We need to get our answer as y is equal to mx plus b. If you want to get your answer as equation in the slope intersection, y has to be by itself. As you can see, y is not by itself. So I forgot to bring the x. This has x. So this times this is negative 0.95x. As you can see, y is not by itself. There is a number attached here. So we have to move this number to the right side. Because it's negative, it means we are adding it to both sides. So we add 5.7 here and we add 5.7. So now y is by itself. So our answer here is going to be negative 0.95x. And then when we add these two, we are getting 7.6. Now it is in the slope intersection. We have y by itself. We have our equal sign. We have our slope. Our slope was initially negative 0.95. That is exactly what we see here. And we have our x and our b, which we call the y-intercept. We got it by adding the 1.9 to this, and that gives us 7.6. This is how we find equation of the line. That is one way of finding equation of the line. I did that by finding my slope. I've forgotten my slope. I wrote this. This is the formula for finding equation. One of them. I wrote this down. Y has to remain as y. X has to remain as x. M was what we saw. We got 0.95 negative. And then this we got it from here. And then this x1 is from here. And then we just distributed. And when we distribute, this is multiplying. It gave us this. This times that gave us 1.9. We want y to be by this. We want our answer to look like this. So we had to move this away by adding it to both sides. And that gave us negative 0.95x. When we added, we got 7.6. That is one way of finding equation of the line. The other way is what James told us. We could have used this straight away. To use this straight away, you need your y, you need your m, you need your x, which we can easily get any of the x from here. We can easily get any of the y from here. And we know m, but we don't know b. We don't see b written anywhere. So in order to get b, which is very important, b here is 7.6. In order to get b, then we have to plug in values for x, plug in values for y, plug in values for m. Based on that, we should be able to find b. So you can decide to choose this first two, or you can decide to choose this. So it doesn't matter if you are using this or you are using that. It will still give you the value for b. So if we want b and we want to use the other formula, which is this. So this is the sense of those who are confused. That's what I'm doing right now is I'm still going to get this equation. To solve it for equation, but this I'm not using this. I'm using this one. I'm using this straight away, and it will still give me the same answer as this. So I've shown you how to use this. I'm showing you a second way you could have used to get the equation of a line. So this second way is use this straight away. The first way, this was what we were using, but our answer had to be in this form. In the second way, we are using this straight away. In order to get this, we need to get y, get n, get x, so that we can be able to solve for b. So I'm going to use any of these to represent xy. This can be xy, this can be xy. I'm using the first one again. I use the second, get the same answer. If I'm using the first one, then my y is 5.7. So I put here as 5.7. My m is what we have already calculated earlier on. We got it to be 0.95. 0.95 has to multiply x. So x corresponding to 5.7 is 2. So I put 2 here. This answer for b. What I've done is I've substituted this here. I've substituted the m. I've substituted x. Now I want b. So I have to multiply the m and the x, and when I multiply this, I'm getting that to be negative 1.9 plus b. I want an answer for b. So since we want answer for b, we have to move away whatever is preventing b from being by itself. That is negative 1.9. So we have to add to both sides. So we do opposite of this, which is add. So add 1.9 here, and then we come and add 1.9 here. Cancel out, and we have b by itself. And when we add 5.7 to 1.9, which is similar to what we had here, 5.7 to 1.9, if we add, we are getting that to be 7.6. So now we have a value for b, but we have to put it in the form of an equation. So now we go back to our original, and this will now remain as y. M is what we got as negative 0.95. X has to always remain as x. Now we have a value for b. Our b is 7. So this is the equation of the line. That's the same thing we got here. So whether you are using this or you are using that to get the same answer, if you want my opinion, this is much shorter. This doesn't involve a lot of work. Here, you are just choosing any of the y, plug it here. If you choose this as your y, then choose its corresponding x. The corresponding x here is 2. Put it in place of your x. What did you get for m? When we did m initially, we got 0.95. So this is your m, this is your x, and b here is what we are looking for. We don't know b. So we have to multiply the m and x to get negative 1.9. And then in order to get b by itself, we have to move this negative 1.9. As you move it to this side, you are adding it. It's negative. So we do opposite sign. Opposite is add. So we add it to both sides. And then this becomes b by itself. And this is 7.6. So now to get the equation of the line, what we just did was to find b. To get the equation of the line, go back here. Y has to stay the same as y. Our m here is the negative 0.95. Bring your m. X has to stay the same as x. And b is what we got as 7.6. So this is the equation of the line. It's the same as what we got here. So that is how we find the equation of the line. So we have the equation of the line, which is this. So from here, that is what you see here. So we are going to close very soon. I know I've taken your time, but that is what you see here. We found our slope, which is m. So this m is not median. This m is the I'm sorry, I won't say that. This m is the slope. This is m here is the slope, algebra slope. So that is negative 0.95. And then from here we have y minus y1, which is equal to all this. So we substituted like I showed you, and we got this. And I've also shown you the second way that you can do this. The y is equal to mx plus b. use any of these. You can decide to use this for your x or y, or you can use this. So I use the x, I substituted the value of x here. I substituted the value of y here, and we know m is 0.95. And we went around it in order to get a value for b. After we got b to the 7.6, we just put the 7.6 here. X has to always remain as x. Our slope is what we got as 0.95, and then y has to always remain as 1, which gave us the same answer. So we are going to end here. When we come back on Monday, God willing, B says that after you have found the equation of the line, now we need to go ahead and draw that equation on a scatter diagram. So we will first draw our scatter diagram, our original scatter diagram, and that is the point, the square that you see. That is our scatter diagram. After drawing your scatter diagram, now this equation which we just did, this equation that we just came up with, we did this equation. We are going to do it like we did in elementary. We are going to find your own x values like 1, 2, 3, all the way to 4, 5, 6, and plug in the value of x here. As you plug in the value of x, you can add to get a y. Plug in the value of x, you add to get y, and that will be the straight line. So that will be the answer when we come back on Monday. So this straight line is as a result of using this equation which we just made up. So if your equation is wrong, then it means that you are going to get B wrong. So we are going to end here.